the performance of GaN-based PFC rectifiers. If we look at the figure of merit for various devices, it is clear that GaN is suitable for high-power applications. If we look at a conventional boost PFC, we want to increase the power output from this. We use interleaving. We want to see if it is better to use GaN or stick with silicon-based MOSFETs for this application. So herein we use available devices from the market, model these devices in Plex, design a closed-loop control boost and interleaved boost PFC, and then draw conclusions as to the efficiency and volumetric gain. Here we have a double pulse circuit to determine the switching characteristics of various devices. This is because the data is not available to us directly, and we use SPICE models from the manufacturer to feed thermals into Plex. We have this boost power stage where we have optimized the design for 1 kilowatt, and we see the various waveforms for input current and THD and power factor. If we look at the losses are predominantly the switching losses. GaN switching losses are much less and the junction temperatures are much less. For the control stage, we have a voltage loop, a current loop, which is then fed to the gate. To see the controller in action, we step the load from 0 to 25% and see the output voltage stabilize itself. We do the same with the interleaved boost controller and design the various components involved. For the controller here, we use a voltage block once again, which is a transconductance type amplifier that is connected to an external compensation network. This generates a compensated voltage error that is then shaped to the input sinusoidal voltage waveform. This quantity is then gained up and then fed to the current controller after subtracting from the respective inductor currents. Note how the current controller was designed using an OTA with external compensation. The output of the current controller is then fed to the PWM block that drives the FETs in the interleaved boost PFC. This is 180 degrees out of phase. We look at the results. We see that for the interleaved boost PFC, the best efficiency is achieved with GaN, and the lowest curve that you see, that is the dotted red, is for the single boost PFC with CoolMOS from Infineon. The losses are dominated by the switching loss, notwithstanding the losses from the diode bridge, which are assumed equal for both the cases. In this case, Infineon has much higher switching losses compared to GaN. We then design our circuit with the components available in the market. Note how the cost of the GaN is much higher compared to the cost of the Infineon MOSFET. The size though is much smaller, and the passives are automatically reduced in interleaved boost PFC, but if we increase the frequency, GaN is much better. In conclusion, the replacement of silicon with MOSFET, GaN affects the power density and the efficiency of the PFC in both boost and interleaved boost topologies. The size of the passives in the circuit as well as the efficiency are improved. However, it is incumbent upon the designer to identify what drives the design, cost or size. For reduced EMI filter and boost inductor, using a GaN FET is much beneficial at the given power level. However, for the same frequency, the incremental gains in efficiency do not justify the use of GaN FETs. In the report you will find more details about the interleaved boost performance and Bode plots for the voltage and current. Thank you.